Picking up where we left off. Exponential equations. The first few exponential equations we're going to solve, we're just going to go back and use common sense methods. And kind of like a plug and chug, a trial and error type method, just to solve these. Because like here, 4 to the x power equals 1/4. We know that 4 to the first power is 4, 4 to the second power is 16, 4 to the third power is 64, and that thing's growing exponentially. The bigger the number we plug in, the higher the 4 to the x becomes. So that tells me that we're going to have to go the other direction. 4 to the 0 power is 1. Think about how when we raise things to negative exponents, we're bringing it to the bottom of the fraction, right? So first off, we know that the 4 is going to have to be to a negative exponent, but negative what? 4 to the negative 1. When you raise 4 to the negative 1 power, you bring it to the bottom of a fraction, it becomes 4 to the positive 1, put a 1 on top, and it does equal 1/4. So x must equal negative 1. And that's, like I said, that's how we're going to solve all these first ones. 1/10 to the x power equals 100. Same thing here. I know that I'm going to have to raise that 1/10 to a negative exponent to flip it over. If I do 1/10 to the negative, all of a sudden we have 10 to a positive. So 1/10 to the negative what's going to be a positive 100? Negative 2. Flip it, that'd be 10 raised to the positive 2, which is 100. So x in this case is negative 2. Moving along. 2 to the negative x equals 1/8. And be careful here because this negative is already built into your equation. 2 to the negative x power equals 1/8. If you want to, you can rewrite that thing as 1/2 to the positive, 1/2 to the positive x equals 1/8. If you want to rewrite it, you don't have to. In order to make 2 to the x equal to 8, then x must be 3. And these are pretty easy. It's just more or less, it's more review than anything. Next up says, and this is the same thing, it's just worded different. Let y equal 5 to the 2 minus x power such that y equals 125. It's telling you what y value, okay? When y is 125, then what is x is what it's asking here. So take that y value, plug it in. 5 to the 2 minus x power. What is the x value that makes that y equal 125? Here's how I'd work this. Ask yourself 5 to what power is going to give you 125. Ignore that the exponent is something ugly here. Does anybody know that 5 to what power is 125? So we've got to make that somehow 3. Well, how in the world can we make that 3? What value of x makes that 3? And if you need to, just say, okay, 2 minus x has to be 3, and we'll solve that. If you need to, the way I would solve it, I'd move x over here, move 3 over here. Negative x, and the reason I'm doing that, negative x would then become positive x, positive 3 become minus 3, so x is negative 1. And some of you, most of you probably could have looked at that. 2 minus what is 3? Well, how in the world do you subtract something from 2 to get 3? You have to subtract a negative because 2 minus minus, that'd be a plus. 2 plus 1 is 3, so x must be negative 1. Compounding interest. A little bit different from your I equals PRT formula that you used to have back in the day. Interest, when you put money into the bank and it starts gaining interest, interest is compounded at different rates. And what I mean that is, let's say you took $1,000 and you put it in the bank, and you earn, let's say, 1% interest on that. Well, here's how this works. Let's say that the word is compounded. Let's say that they compound that interest once a month. What that means is at the end of the month, they're going to take that $1,000 and they're going to take 1% of that 1,000, and you earn that in interest. They're going to take that 1%, they're going to put it with that 1,000, and then not only are you earning interest on the 1,000, but you're earning the interest on the 1,000 and what is 1% of the 1,000? $10. Not only are you earning interest on the 1,000, but now you're earning interest on $1,010. Then after another month, they're going to take 1% of that, which will be $10, 2010, which will be $10.10. And they're going to take that $10.10 and add it on, and now you're earning interest on all those. That makes sense. The I equals PRT assumes that interest is just earned once a year. Okay, so this is actually how the things work. Interest is compounded sometimes monthly, sometimes daily, sometimes quarterly, which would be once every 3 months, 4 times a year, semi-annually, twice a year. So it all depends on how do banks around here actually do that. I don't know. Ask them sometime. I bet your bank teller won't be able to tell you, but you can try it. Here's your formula, and if you want to write this down, this will be used for several of your homework problems. A, which is the amount of money after interest. Okay, it actually adds it together for you. A equals P times parentheses 1 plus R over N raised to the NT power. P is your principal, which is the amount of money you're investing. R is the interest rate, and that rate cannot be as a percent. Like if it's 2%, you would have to change that to 0.02, move your decimal over twice before you plug that in. N is the number of times per year that your money is being compounded. The number of times per year that your money is being compounded. And you think that it won't make a difference, but it really does. I'll show you in a second a chart about whether your interest is compounded annually, twice a year, 4 times a year, 6, 8, 12 times a year, daily, 365 times a year, the amount of extra money. Because think about it, when it's compounded more often, you're earning interest on not just what you invested, but you're earning interest on your interest if it's compounded more often. So A equals P times 1 plus R over N raised to the NT power. And T, I didn't say that. T up here is the time that you leave it, how many years. Okay. So let's work a problem. Find the amount or future value when a principal of $20,000, you're investing $20,000 at 6% interest compounded daily for 3 years. And you want to know how much money do you now have. It's all these first problems is just plugging in. The amount of money that you're going to have is equal to principal, that's how much money you're investing, $20,000. 1 plus the rate, 6% interest, so we write that as how much? Good, 0.06. Divided by what? Because we're compounding it daily, which means 365 times per year. Raised to the NT power, N was 365 times 3 years. We plug the whole thing into our calculator. Okay, let's type it in. Got $20,000. Get your calculator turned on. $20,000, parentheses. Watch how I type this in. You got to be real careful if you're using one of these. 1 plus, you're going to have to put this fraction in parentheses as well. I don't know. It might work without. It probably would. Because it knows order of operations. It would do that first anyway. I'm not going to take any chances. Raised to the, now this is important. Put that in parentheses. 365 times 3. Because if you don't, try to think ahead. If you don't, it's going to do exponents first. And if you don't put that in parentheses, it's going to raise it to the 365 power first, and then it's going to multiply the whole thing by 3. The exponent is what's being multiplied by 3. I got $23,943.99. So over that course of 3 years, your $20,000 investment earned nearly $4,000 extra in 3 years. That's pretty good investment there. But here's the thing. Yeah, right. You're not going to get a 6% interest rate on anything. Unless, here's how the economy works. This is going off on a tangent here. The only way that you're going to get a 6% interest rate is if the economy is so slow, or excuse me, let's say they won't need to invest money. Maybe if the economy sped up, because they want you to invest money, they're going to raise interest rates that you're going to earn. They want you to invest money instead of spending it. So if they want you to invest money and put it in the bank, then they're going to jack up interest rate. And that's how it works. The economy is a roller coaster. Ups and downs, highs and lows. You'll learn this in economics. And anytime the economy's here, you know what they actually want the economy to do? Slow down. They really do. You would think that, well, no, you want the economy going great. You want it to be, just as fast. You want everybody selling, everybody to, no, actually, if the economy gets so high, they want to bring it down. Look at the Great Depression. Now we're getting into history. Look at what happened right before the Great Depression. Economic boom. Just everything was doing awesome. You look back at the 20s and how good things were going. Here's your rule. The higher your economy gets, the lower it's about to get. The better things are right now. So what do they want to do? They would rather the economy look like that and just kind of stay constant. Because anytime you have economic boom, you're fixing to have economic bust usually. That's weird that it works out like that. But that's off on a complete tangent. You're probably not going to get a 6% interest rate. Here's your chart of what I was talking about. Here's a $10,000 investment. Compounded annually, once a year, and see what happened annually. $11,200. You earned $1,200 on that investment. Quarterly, earned a little bit more. Monthly, daily, hourly, earned. You see the difference. Annually versus hourly, you earned 74 extra bucks, nearly 75 extra dollars, just because of the way it was compounded. Same interest rate. It was compounded different, you earned extra money. And then you get down to what's called continuously, which is really fast. Not by the second, not by the millisecond, but even faster than that, continually. Pretty much as soon as it's compounded, it's immediately compounded again. This continuous compounding involves a number called E. Here's your new pi, I guess you could say, if you ever worked with E. E is also an irrational number, just like pi, and this E appears a lot in mathematics as well. Here's your first example. Anytime you have continuous compounding of interest, this number E appears. E is about, same way pi is about 3.14159, ... E is about 2.718, ... It is also an irrational number, continues forever and ever. When we deal with, we're going to talk about radioactive decay, growth and decay and stuff here in a second, it also involves this exact same number. But anytime you have like this exponential growth, this really fast growth going on, it's going to involve this. Here's your formula for continuous compounding, called APERT. If principal is invested for T years and is compounded continuously. Now, if it's compounded annually, semi-annually, all these others, you're using the formula we just talked about. If it's compounded continuously, A is equal to the principal times E raised to the RT power, APERT. The principal times E raised to the RT power, to where E is 2.718. Compounded continuously. Here's your first problem. Find the amount when a principal of $5,600 is invested at 6 1/4 annual rate, compounded continuously. We like seeing that because we can use this really simple formula. This is actually a whole lot easier than the other one. So the amount of money that you're going to have is going to equal the principal, which is $5,600, times E. And honestly, you can go ahead and leave it in as E, and I'll show you in a second on your calculator where to find E. Raised to the, okay, careful here, 6 1/4%. Here's the mistake a lot of people is going to make. They're going to change that to 6.25 and plug that in. You did not change from percent to decimal there. You changed your 1/4 to a decimal, but you did not move any decimals. That makes sense. To change a percent to a decimal, that decimal must be moved 2 places to the left. So you're going to plug in what? 0.0625. If you plug this in, you're going to get a really high number because that's saying you're getting 625% interest. You're probably not going to get that. Okay, that's pretty high. So if you get just an unreasonable answer, more than likely something like that happened. So you've got e raised to the 0.0625 times 9 months. There's another issue. Both of these formulas are built on years, not months. So we've got to somehow turn nine months into years. Well, 9 months is not a full year, but I believe it's this fractional piece of a year because there's 12 months in a whole year. So you're going to invest it for 9 out of 12 months or 3/4 of a year, or to use your calculator, 0.75. So there's what you're typing in. And again, here's how you do it. Move it back over here. Is it, oh, 5 years. I didn't notice the 5 years and 9 months. Thank you very much. I missed that. Since it's 5 and 3, yeah, thank you. 5 years and 9 months, which would be 5.75, not just 0.75. I missed that. Now let's try that. Let's just make sure you always awake this one. 5,600 times e raised to that power. For some reason, I think it's crazy. Honestly, I think they just didn't have anything else to put on the calculator, so they did this. Look above the ln button. Y'all see e to the x power? There's your e. Or, look above that division symbol. It's another e. They put 2 different e's on the calculator. Let me tell you the difference. If you want to raise e to a power, you can use this one. And it goes ahead and puts the power up there for you. If you want to just use the number e, you can use that one. Well, can I just do this and use a caret? Yes. I don't know why. But just to save me from having to push one extra button, I'm going to use that e. It goes ahead and puts the caret in there for you. So e raised to the 0.0625 times 5.75, enter. $8,021.63. $8,021.63. And again, that's not the amount of interest. Make sure that you know A stands for the amount of money that you're going to have after that investment. Okay. Here's another type of equation. And notice the form up here. A equals A to the 0, e to the RT. That is your APERT formula. Okay. APERT also works for, and it's weird that you use the same formula for an investment compounded continuously and then a radioactive decay. It's the same formula. Identical. Now, here's well, it gives you a pretty good explanation here. Here's what we mean by radioactive decay. It says, finely chipped spear points shaped by nomadic hunters in the Ice Age were found on the scene of a large kill in Lubbock, Texas. From the amount of decay of carbon-14 in the bone fragments of the giant bison, scientists determined that the kill took place 9,833 years ago, according to the National Geographic magazine in December 1955. Carbon-14 is a radioactive substance that is absorbed by an organism while it is alive and begins to decay upon the death of an organism. And I'll go ahead and elaborate from that. And they believe that you can take the amount of carbon-14, and if you know the half-life, which does everybody know what half-life is? It's a video game, right? But on top of that, you know what else half-life is? Half-life is the amount of time. Let's say that you have 10 grams of carbon-14. Half-life is the amount of time that it would take those 10 grams to go to 5 grams. That's all half-life is the amount of time it takes something to decay in half. That's its half-life. Makes sense why they call it half-life now. So it says here the number of grams of carbon-14 remaining in the fragment of charred bone, because here in these subsequent problems or in these other problems, you're going to have some half-life type problems on these too. They plugged everything in. They actually just give you a formula. They took an A0 is 3.6 e to the RT A. But let me describe all the pieces of this. A will be the amount of carbon-14 you have at some point. A0. Let's talk about that subscript 0. And that's a little 0. It's supposed to be like A with a little 0 down here. For those of you that are taking physics now, you already know what I'm about to say. A0 is a starting point. Anytime you have a subscript of 0, that's your start. Okay? V0 in physics, anybody know what that is? Initial velocity. That's the velocity that you start with. S0 is your initial position. Okay? A0 is the amount of carbon-14 that you're beginning with. So we're going from A0 to now we have A left. R is the rate of decay, and T is the amount of time it takes to get there. And E is 2.718. It's a number. So it gives us this formula. A equals 3.6 e to the RT power, where R is this funny number here. Scientific notation, 10 to the negative 4 power. Take your decimal, you're moving left 4 times. So you've actually got A equals 3.6 e to the negative 0.00121 T. That makes sense. Find the amount present initially, and find the amount present after 9,833 years. Now, if you listen to what I said a while ago, the initial amount is pretty easy. The initial amount, if we want to do it the hard way, your initial amount is the amount of carbon that you have when time is 0. At your start point, but plug in 0. Do you see what happens to your exponent? Goes to what? 0. E to the 0 power is 1. So at time equals 0, how much is present? 3.6, right? Didn't I tell you that's the initial amount right there? So that's how much we start with, and then we end up with, after 9,833 years, we end up with how much? We're just plugging that in for T. That's all you're doing on these problems. So that would be 3.6 times E, and since I'm going to raise it to a power, I'll use that one, to the negative, I think that's supposed to be a decimal here, isn't it? Oops. 0.000121 times 9833. Can y'all check me on this? Because I feel like I might have plugged it in wrong. 1.09 grams. Is it in grams? I think. Let's go back and check. Yeah, number of grams. So about 1.10 grams are left after 9,833 years. So you went from 3.6. Now, question, I discussed half-life a while ago. Is that beyond its half-life? Yeah. I would say its half-life was somewhere around, well, here you go. Try this. Here's the graph of what we just did. You can kind of tell what the half-life is by looking at this graph. There's the bison that got killed. Hate that. So we started with 3.6, and its half-life was when it hit about 1.8. This is in thousands of years. So I'm looking at about 6,000 years would probably be its half-life. So you see, yeah, 9,833 years is beyond that half-life of it. Okay. Any questions? Logarithms. The moment we've all been waiting for. What is a logarithm? This is confusing. Let me read it, and I'll prove to you this is confusing. For a is greater than 0 and a is not equal to 1. This reads like a math book. If you want to try to open up a pre-calculus, calculus book and learn how to do this stuff, this is what you get. For a is greater than 0, okay, I'm good there, and a is not equal to 1, the logarithmic function with base a is denoted by f of x equals log base a of x. Now, I do want you to learn that from it. F of x equals log base a of x. That's how you read that. This is the base of the log. And what they're telling you with all this stuff, A has to be greater than 0, and A cannot be 1. You'll learn why in just a little while. That is true if and only if, in which, by the way, we all know that that is y. Y equals log base A of x. That is true if and only if. That's how you break down if and only if, or shorten it. A to the y power equals x. Y equals log base A of x if and only if A to the y power equals x. In layman's terms, a logarithm is simply an exponent written in a different way. That is all a logarithm is. And what I'm going to show you first is how to rewrite these things. And that's what this is. No, let's not evaluate them yet. I want to rewrite some of them. If you've got the exponential equation, 3 to the second power equals 9. Have y'all ever dealt with logs? Yeah. Trees. Fallen trees. 3 to the second power equals 9 can be written in logarithmic form. This is exponential form. In logarithmic form, this exact same equation, 3 to the second power equals 9, can be written as log base 3 of 9 is equal to 2. A logarithm is simply taking an exponential equation and rewriting it. Log base 3 of 9 equals 2 is the same thing as 3 to the second power equals 9. 4 to the negative 2 power equals 1/16. If and only if can be written, that's a biconditional. We'll talk about that in geometry. If somebody will try it, log base 4 of equals. Here's how I remember it. What do I call this? This 3 right here. That's the what of the log? The base. The base of the log, well, when you're dealing with an exponent, what's that called? The base. The base of the exponent and the base of the log is the same number. And all you're doing with the other two numbers is this is the argument of the log, and this is what it's equal to. You're kind of flip-flopping them. Log base 3 of 9 equals 2. Log base 4 of 1/16 equals negative 2. And sometimes you'll have to go backwards on your homework. You've got some to where they'll say log base x of y equals z. And they'll want you to rewrite that in exponential form. The base of the log is the same thing as the base of the exponent. This number over here that your log is equal to is your exponent. So this would be x to the z power is equal to y. That's how you rewrite it. Everybody good? That right there, what I just showed you is hands down the most important thing in this entire chapter. You have to be able to go from logarithmic form to exponential form, from exponential form to logarithmic form. What is the purpose of logs? Why do we even have logarithms when it's simply that other stuff rewritten? Why do we even have logarithms then? We use logarithms to solve exponential equations. Look at this equation. 2 to the x power equals, we're good with 4, right? We're good with 2 to the x power equals 8, but what if I say 2 to the x power equals 6? Oh, that's easy, that's 3. No, that's 2 to the third power is 8. 2 to what power is 6? I don't know. We're going to solve these later on using logarithms. That's the whole purpose of logarithms, is to solve exponential equations. Equations where you have x's and the exponents. Evaluating the logarithms, and this is what I expect to see ACT. Prior to seeing a logarithm, you would look at that and say, there is absolutely no way, I have no idea, skip it. This will be one of the easiest problems that you have on your ACT. If you know how to rewrite this thing, if you want to put equals x, you don't have to. But if you want to put equals x just to where you can think about rewriting this, the base of your log is the same thing as the base of your exponent. We're going from logarithmic form to exponential form. The number that it's equal to is your exponent. The argument of your log is what your equation is equal to down here. Isn't that easy? When you're dealing with this logarithmic equation now, all you're saying is 3 to what power is 9? What's this equal to? 3 to what power is 9? 2. And 3 to the second power equals 9. That's all that is. That makes sense, right? So log base 3 of 9 is 2. Log base 2 of 1/4. You see that what we're doing now is exactly what we started out the day with. We're saying 2 to some power. 2 to what power is equal to 1/4? Well, what's 2 to the second power? 4. We're close. But we need 1/4. How do we get that 4 on bottom? Negative 2. 2 to the negative 2 power. Put it under a fraction bar, or over a fraction bar. Bring that to the bottom. That's 1/4. So log base 2 of 1/4 is negative 2. Okay, so we understand logs a little bit now. Log base 1/2 of 8. And notice, again, this base cannot be 1. This base cannot be 0. It can be a half. We're saying to ourselves here, 1/2 raised to some power is equal to 8. Again, you're going to have to flip it, so it's got to be a negative power. That's going to take that 1/2 and flip it over and make it a 2. 2 raised to what power is 8? So let's try that. 1/2 to the negative 3. Just to check ourselves. To get rid of the negative, we're going to flip it, make it positive. That does equal 8. So 1/2 to the negative 3 power does equal 8 logarithm. There's no number. What in the world? This is called a common log. Good job. A common log. Anytime there's no number, it's understood to be 10. On your calculator, if you'd like to look, you have a log button. This log button is a common log. Okay? So if you want to, you can type this one in. Log 1,000. It's 3. But you really don't have to type it in, because all you're asking here is 10 raised to what, because again, the base is 10. 10 raised to what power is equal to 1,000? Well, 10 to the first is 10, 10 to the second is 100, 10 to the third, 1,000, right? So that's the reason it's equal to 3. 10 to the third power does equal 1,000. We follow how to evaluate logs. Ask questions if you got them. Good? If that was a common log, this is called a natural log. You know what the natural log base is? Anybody want to take a stab at it? Because remember, bases can't be 1. Does it make sense why bases can't be 1? Let me give you a problem, and then we'll get back to this. If I gave you log base 1 of 14, it makes sense now why bases can't be 1. 1 to what power is going to give you 14? I believe 1 to any power is just still 1. You see now why bases can't be 0 either? 0 to what power gives you 14? Well, 0 to any power is 0. Natural log. A natural log is simply a logarithm. If you want to turn this ln into log, a natural log is a logarithm with a base of e. There it comes again. 2.718. This number is so special that we dedicate an entire category of logarithms to it. A natural log is a log of base e. So this problem is the same thing as saying log base e of 1, which we can do in our head, but you don't have to. Look, there's an ln button. Your goal for mathematics, and this was my goal in college, is to know what all those buttons mean. You got so many buttons on that calculator. Hey, we've knocked a lot out this year, right? Today, just today, we've knocked out those 2. Look right above ln. You see now why that e to the x is right above ln. So log base e of 1, or natural log of 1, is equal to, anybody want to take a try at that? E to what power is 1? 0. Anything to the 0 power is 1, right? So e to the 0 power is 1. The natural log of 1 is 0. What's the log of 1? That's common log. 10 to what power is 1? 0. What's log base 3 of 1? 0. Any kind of log of 1, whether it be log base 3, log base 5, log base 1,000,000, log base e of 1 will always be 0, because anything you raise to the 0 power is always 1. Okay, moving on. Natural log of -6. Now we're getting into that whole domain range stuff again. The natural log of -6, somebody type that in. Let's get the calculator out, please. Error. Why? Yeah. This is a base of e, right? You're asking yourself, and if you need to put the e down there, put it. Ln is a log base e. You're saying e to what power is -6? How do you raise a number, a positive number? Let's do a different one. Let's do log base 3 of -6. How can you raise a positive number to some power to give you a negative number? A lot of people's like, well, that's easy. You just raise it to a negative exponent. You do like 3 to the -4, and that's going to give you a negative number, right? No. If you raise a positive number to a negative exponent, you bring that to the bottom of a fraction. It's still positive. So is there any way possible to raise a number to a negative exponent to give you a negative number? No. You know why? 3 to the x power. What did that graph look like? Looked like that, didn't it? Did it ever cross this axis? Did it ever go negative? No. There's no way that you can raise any positive number to any power to give you a negative. That y value will never be down here. So that's the reason any logarithm, log base e, log base 4, log base 10, any logarithm, you cannot take the log of a negative. Never going to have an answer. You can't raise a positive number to any power to give you a negative. So later on when I ask you what's the domain of log x, can you take the log of 0? Think about it. Log base 10, right? Is there any way you can raise 10 to a power to give you 0? 10, yeah, that's right. 10 to the 0 power, right? 10 to the 0 power is 1. It never hits 0 either, does it? So therefore, your domain for logarithms is going to be greater than or equal to 0. Or greater than 0, not greater than or equal to. You can only take the log of things greater than 0. Which brings this up. Graphs, domain range, we'll probably finish this and then stop for the day. Sketch the graph of y equals 2 to the x power and y equals log base 2 to the of x on the same coordinate axis. And there's a reason for this, and this will be a good review for you too. Y equals 2 to the x power, we've already done that. That's an exponential equation. 2 to the first, 2 to the second, 2 to the third, 2 to the 0. We know what that's going to look like. It's going to be like that, right? We did those. Now, what about log base 2 of x? Y equals log base 2 of x. That's going to be a fun graph, right? How long are we going to graph that? Let's see. What would you do? Would you plug in x's? Because if you plug in x's, let's say x is, now you could, let's say x is 1. Where's y? 0. Because 2 to what power, 2 to what power equals 1, well, that'd be 0. You could plug in 2 for x. 2 to what power is 2? But do you know the easy way of doing it? Plug in y's. Right? Because if you plug in y's, you're doing, okay, when y is 2, you're saying 2 to the second power is x. So when y is 2, then x is 4. When y is 3, x is 8. Hang on a second. Does that look similar to that? What's the relationship between y equals 2 to the x power and y equals log base 2 of x? Does anybody know? Think back to old stuff. This might help. That's log base 2 of x over there. Here's y equals 2 to the x power, xy. When I plug in 0, I get 1. When I plug in 1, I get 2. When I plug in 2, I get 4. When I plug in 3, I get 8. What's the relationship? Somebody remember the word? They are blanks of each other. Not conjugates. Close. We're getting there. It's an I word. They're inverses of each other. An exponential equation and a logarithmic equation are inverses of each other. What are inverses? Plus 3 minus 3 are inverses. Squared square roots are inverses. Logs and exponents are inverses. So it kind of goes along with what I told you a while ago. Here in a second, when we start solving exponential equations, how are we going to solve it? By using its inverse, by using logarithms. Here's your graph. I'm not going to go through the trouble of graphing it when I've got them right here. Y equals 2 to the x power. We already knew what that was going to look like. Y equals log base 2 of x. Looks like this. If you don't remember, when you have inverses, this will be on ACT, guys. When you have inverses, they're symmetrical across this y equals x line. So if 2, 4 is on one, 4, 2 is on the other. If 0, 1 is on one, 1, 0 is on the other. So if you want to graph two inverses, well, graph your original function, then just flip-flop all your x's and y's. That's what an inverse is. The inputs and the outputs change places. What used to be x is now y. What used to be y is now x. There's your two graphs. Okay. To graph y equals log base 1/3 of x in this status domain and range. If you wanted to, you could actually do, let's see, again, y equals log base 1/3 of x. If you wanted to graph its inverse, which is actually, let's say, switch your x's and y's. We'll get to this more later on. And then change forms. Remember how to change forms? Base raised to this. So this is 1/3 raised to the x power equals y. If you wanted to graph that and then flip it, you could you would have the graph of y equals log base 1/3 of x. So this t-table looks like that. Because this t-table is going to be so much easier to make. Plug in 0, 1, 2, and 3. 1/3 to the 0 power is 1. 1/3 to the first power is 1/3. 1/3 to the second power is 1/9. 1/3 to the third is 1/27. Well, it's shrinking, isn't it? Let's go the other way. -1. 1/3 to the -1 is 3. 1/3 to the -2 is 9. So to graph this, don't graph all those points. Graph the points, instead of 0, 1, plot 1, 0. Plot 1/3, 1. Plot 1/9, 2. Does that make sense? They're inverses. And you can check yourself. Log base 1/3 of 1/3, is that not going to be 1? Because 1/3 to the 1/3 to the first power is 1/3. But like the same as before, I'm not going to go through the trouble of plotting all those. Save time. Here's the graph. It's what it actually is. Remember exponential decay. It is this, something like this. Exponential decay problem that's been flipped across that line y equals x. Okay. Moving on. So a logarithmic function has the following properties, and notice it's very similar to what we talked about with exponential graphs. The function is increasing for a greater than 1, decreasing between 0 and 1. The x-intercept, instead of being 0, 1, like it was for exponential, is now 1, 0. Graph has a y-axis, which is a vertical asymptote. Before it had an x-axis, which was a horizontal asymptote, that 2 to the x power did. Domain and range, notice they're flipped. Before exponential functions, domain, everything. Range was above 0. Notice that you've got domain for the new one is above 0. And the range is negative positive infinity. And the function is still 1 to 1. Okay. This was 1 to 1. This was exponential function. This was 1 to 1. Its inverse will also be 1 to 1. Real fast transformations. We've discussed them 1,000 times. Okay. We've over and over and over. The parent function of this would be y equals log base 2 log. Again, parent function log base 2 of x. There's one transformation here. You're taking your log base 2 of x and you're shifting it where? Right. Careful, right one. Opposite. There's the two functions. That's it. You're going to learn that if you know how to do transformations for that first time, it's going to make your life a whole lot easier throughout pre-calculus because there's lots of transformation taught from here on out. And here you've got 1, 2, 3 transformations. The same log base 2 of x that's been shifted. Y'all help me out. What does this do? Left 3. What's the 1/2 do? This is ones we have issues with, right? It's not inside. It's not horizontal. It's vertical. So what's it going to do? Stretch or shrink? Shrink by 1/2 vertically. And then also the negative is not inside with the x, so it's going to flip it vertically. So we had a shift left 3. Yeah, here's your original. Had a shift left 3, had it shrunk, had it compressed by 1/2, and we had it flipped up and down. So here's your new negative 1/2 log base 2 of x plus 3. Any questions?